Hmm. Now we'll just run through the syllabus, the detailed syllabus. So you see your entire syllabus is divided in 5 units or 5 modules as such. So the first module or the unit 1, this is devoted for the two major topics from your syllabus, that is properties of fluids and fluid statics. Actually, these two are different topics, but they are combined together. The properties of fluids and the fluid statics. So what we are going to learn in this module is the basic definitions of fluid properties, and then the Newton's law of viscosity, concept of continuum, the classification of fluids, how we are going to classify fluids, what are different ways by which you can classify the fluids. So that part we are going to cover up to this point. So this part is properties of fluids, basically introduction to the basic properties. And from this point onward, we are going to study the statics part, fluid statics. So in engineering mechanics, you studied what is statics and dynamics, right? So there you analyze the system as a whole. Like for example, you must have calculated what are the forces on let us say a sphere which is resting on ground, right? So that type of static problems you have solved. Similarly, in fluid statics, what we are going to do is we will calculate what will be the forces acting on the structures when the fluid is at rest and is in contact with some surface. So that type of analysis. Now the fluid static analysis is what you can say pretty analogous to what you studied in engineering mechanics. So just now before some time I said you must have the basic understanding of engineering mechanics. This is the reason why I was talking about. Is it clear? So fluid statics will require the basic understanding of engineering mechanics. Fine. So in this, we'll study the definitions like what we mean by the body force and surface force. Right now, there is no point in talking more about types of forces. As the course progresses, you will come to know what we mean by body force, surface force. Then the Pascal's law, you might have studied even in 11th or 12th physics also. Anybody knows what is Pascal's law? Any idea? Hello.
So it was like the pressure is same throughout the fluid. Like if it's P1 is equal to P2, the pressure
So
down the
when
fluid
you
and the
studied
pressure
this
in
in
the
12th
10th
or
stand,
10th?
11th I guess, 10th or 11th. I'm not sure
So
about that.
then I need not have to spend more time on this part. We can run through this. So Pascal's law is basically related to when the fluid, in case of a static fluid, the pressure or intensity of pressure is same in all directions. This is what the Pascal's law talks about. Here we will prove this law in our course. Fine. Then the next is the basic hydrostatic equations we'll derive. Then we'll study how to calculate or how to find the forces exerted by a static fluid. We call it as hydrostatic forces or the total pressure. We'll study how to find out these forces on plane surfaces as well as curved surfaces. Like for example, in case of dam, because of the static fluid, there will be some the force exerted on the gates of your dam, right? So there we'll try to find out the hydrostatic pressure or the forces acting on the gate. Fine. Then we'll also talk about some of the basic concepts like buoyancy and stability of floating and submerged bodies. This part also you must have studied in maybe from 10 to 12 somewhere you must have studied this. You may be calling it as buoyancy. I'm just calling it as buoyancy. And the stability of bodies which are either floating on the surface or submerged, partially submerged or fully submerged. Fine. So all that part will be covered in the first half of module 1, which is the properties of fluids and fluid statics. In syllabus, you may think that this is hardly given in 3-4 lines, but it will take even if I go at a very fast speed, then also it will take minimum 6 lectures to cover this. Fine. Then the second half of module 1 will talk about the fluid kinematics. Now, what do we mean by fluid kinematics? You must have studied kinematics in engineering mechanics. What do you mean by kinematics?
Related to motion.
So So there you have seen the objects which are in motion, and you analyze the forces when the object is in motion, right? But in case of fluid mechanics, we'll analyze the forces, or we'll analyze the situation when the fluid is in motion. Understand the difference between what you did in engineering mechanics and what you are going to do in fluid mechanics. So the fluid kinematics is essentially when you are analyzing the situation when the fluid is in motion. Now again, there are further classifications, whether you consider the forces which are causing the fluid motion or whether you neglect the forces which are causing the fluid motion. So depending on that, you can further divide this fluid kinematics part as well. Fine. So in fluid kinematics, we will talk about the basic approach of fluid flow description. There are two ways by which you can describe the fluid motion. One is called as Eulerian approach and another is called as a Lagrangian approach. You must have heard these words in mathematics, Euler and Lagrangian, right? So these two approaches we are going to discuss in fluid kinematics. Then the two most important parameters whenever we talk about fluid motion, that is the fluid velocity and the acceleration. This thing we are going to study in fluid kinematics. We'll try to find out what will be the velocity maybe in 2 dimensions or 3 dimensions, and the acceleration components maybe in 2-dimensional flow or 3-dimensional flow, something like that. So we'll learn how to calculate the velocity and acceleration using these approaches, Eulerian approach and Lagrangian approach. That part will be covered in fluid kinematics. Fine. Then there are a few more definitions in the same topic called as a streamline, streak line, path line, stream tube, and we'll classify the different types of flows. Now see the difference. We are not talking about the classification of fluids. We are talking about the fluid flows, types of fluid flows. So how you define the different types of flows, like what we mean by, for example, I'm just talking about what is 1-dimensional, 2-dimensional, 3-dimensional flow, what is laminar turbulent flow, what is compressible, incompressible flow, what is rotational, irrotational flow, something like that. So all that types of classifications, or what is steady, unsteady flow, what is uniform, non-uniform flow, all those classifications of flows will be covered in this topic itself, fluid kinematics. Clear? Again, in the same topic, we'll talk about one of the most important aspect of fluid mechanics. We'll talk about the basic definitions, like what we mean by control volume and control surface. So part of this you already studied in thermodynamics. Can anybody tell me what you mean by control volume?
Have you applied in the open system? It is in the open system. Basically in which the mass and the heat interactions take place.
So that is in the context of thermodynamics, right? Yeah. So how we are going to use the similar kind of concept in case of fluid, that we will study here, control volume. So there are basically two types of approaches. The one approach which we have used in engineering mechanics, which is called as, anybody know what is the approach we have used in engineering mechanics? What that approach is called as?
So, sorry, please repeat.
You have analyzed the situations, or what you can say, the systems in engineering mechanics, right? So you have used typical approach there. For example, I'm just giving you hint. Let us imagine you have a ball which you throw in the air, right? And it is following some trajectory path and coming down to the earth, right? So you must analyze this entire situation, right? So what is the approach you have used?
Conservation of energy.
That is the principle behind. I am talking about the approach.
Okay, first we analyze the kinetic and potential energies, number of energies acting at the first state and the number of energies acting at the second state, and then we equate anything like that.
Okay, now it will be too early if I talk further about the same topic, but only to give you the what you can say, the idea behind the two different types of approaches. I am just explaining it further. So the approach which you have used in engineering mechanics is called as a system approach. Are you getting me? I said the approach which you have used in engineering mechanics is called as a system approach. So imagine the situation just now I talked about, that you are throwing a ball in the air you are following the entire ball as a system, right? So whatever the analysis you are doing, it is totally applicable for the entire ball, right?
Yes.
sir.
So this is
Yes.
called as a system approach. Now, come back to fluid mechanics. Now imagine, let us say the water is flowing through a pipe, right? Now tell me, is it possible to apply the system approach for this case? Water is flowing through a pipe. Now tell me, is it possible to apply system approach?
No, sir.
Why?
No, sir.
Why?
Because the fluid will be flowing continuously,
Ah,
so we cannot take it as a system.
so
Ball was a
now,
concrete object. Ball was a
now,
concrete object.
now throughout your what you can say, the engineering career, now you should not forget these two words which I am talking about, system approach and control volume approach. In case of system approach, we follow a fixed identifiable mass throughout its motion. Is it clear? I repeat, in system approach, we follow a fixed identifiable mass throughout its motion. Now, in case of fluid mechanics, it is very, very difficult, or it is almost impossible to follow the same fixed mass throughout its motion. Is it clear?
Yes.
So
Yes, sir.
that's why we use control volume approach in case of fluid mechanics. Is it clear?
Yes, sir.
So what we'll do is we'll simply take the domain which will cover your inlet of the pipe, outlet of the pipe, and the wall which is surrounding, right? Surrounding wall of that pipe, and we'll take this fluid as a control volume. And we are least bothered of how the fluid is behaving inside. So what we want to study is what is the end effect, or what is the net result of fluid passing through the inlet and going out of the outlet. So that is what our area of interest is, right? Getting me or not? So I am not bothered of how it is, means how the things are happening inside. So I am not bothered of. I just want to see what is the effect at the boundary, right? Boundary of our control surface. So that type of approach is called as a control volume approach. Now you see their control volume, words like control volume, then the control surface. I hope you must have studied these things in thermodynamics, but I doubt whether you have used those concepts for selecting the control volume and actually analyzing the situation. I doubt. At least for at the time of using steady flow energy equation, you must have used this, or not?
Yes. Yes, sir.
So the idea is you should be in position to select the control volume. ठीक है, वहाँ पे तो simple situation रहेगा thermodynamics में, but in case of fluid mechanics, it will be you who will decide how to select the control volume and what should be included in the volume and what should not be included in the volume. All that as an engineer, you should be in position to decide. ठीक है? Then beyond this, then we'll introduce a few more concepts like what is the circulation. These are typically related to the fluids in motion, fluid kinematics. Circulation, vorticity, means what is the rotational effect of the fluids. These are definitions and their effects we will study. Then next, understanding of differential and integral methods of analysis. Again, there are two approaches for studying the fluid flow. One is called as a differential aspect. We'll use the differential equations. Differential equations, like for example, I may derive the differential equation, mass conservation equation, or the momentum equation, right? And that differential equation we can use for the analysis. And there is one more approach called as the integral approach or integral methods, right? You must have studied this in mathematics, integral approach. So both approaches we are going to study in our entire syllabus. There is specific topic called as the Reynolds transport theorem. There we will use this integral application for analysis. Fine. Then going beyond this, definitions and equations for a few more terms or properties like what is stream function, velocity potential function, and we'll define those for the different coordinate systems, like how it will be for a simple rectangular coordinate system, that is Cartesian coordinate, and how it will be for the cylindrical coordinate. And I talked about this rotational, irrotational flows, and how to decide whether the flow will be rotational or irrotational will be based on these properties like velocity potential, stream function, all that stuff. Okay. And then few more definitions, like this will be actually very superficial treatment for the last line, that is definition and equations for source, sink, irrotational, vortex. This is the introductory part. But up to this point, there will be full treatment, theoretical as well as the numerical treatment will be given for the fluid kinematics. Okay. A lot of numericals will be solved during this. So I'm supposed to cover this module 1 or unit 1 in 12 hours. The first time I am teaching this subject with 3 lectures per week. For other batches, we had 4 lectures per week. Now it is more challenging for me as a teacher also to teach these 2 sub modules in 12 hours. However, I'll try my level best to finish this content in 12 hours. Fine. So that's all about module 1. Now the second module, module 2, is entirely devoted for the fluid dynamics part. So what we'll study is again the fluids in motion, but this time we'll consider the forces which are causing the fluid motion, right? And the whole fluid dynamics part will be covered in 8 lectures. Fine. So I am not going in details of whatever the syllabus is given. You can read. I am giving you 2 minutes, just go through this paragraph, and if you have any doubt you ask, otherwise we'll go to the next module. You just read, at least at the end of the lecture you will have some typical words which are only related to the fluid mechanics subject. For example, this Reynolds transport theorem, then the conservation of mass, energy, momentum principle, Bernoulli's equation in fluid flow measurement, and what is the Spitot tube, venturimeter, orifice meter, nozzle meters. These are actually the applications of Bernoulli's equation, and basically the flow measuring devices. Then the differential equations for the control volume. Just now we talked about control volume. And then the mass conservation equation in 2 and 3 dimensions in rectangular coordinates. We are going to derive those equations. Then the Euler's equation in case of 2 and 3 dimensions, and the derivation of Bernoulli's equation from Euler's equation. And up to this point, it is somewhat simple task. This part is somewhat simple. This one is fundamental. Even those who are, especially those who are looking for higher studies, maybe for MS in maybe in thermal fluid, for them this is very important part. First one. Then this, up to this point, it is very easy. And now from this point onward, this part is again difficult. The Navier-Stokes equations. We are directly going to take the Navier-Stokes equations. We are not going to prove these equations. The proof of these equations is covered in the master's course. Suppose if you are doing masters in thermal engineering or fluid engineering, that time you are supposed to derive those equations. But for our case, we will take those equations without proof, but we will discuss each and every term in these equations and their significance, and then we'll go ahead and we'll learn how to simplify those equations for typical situations like exact solutions of Navier-Stokes equations for viscous laminar flow. A simplified case, viscous laminar flow, and that too for 2 parallel plates, flow between 2 parallel plates. One is when both plates are stationary, we'll call it as chord flow, and when one plate is moving and one is stationary, they are the type of Poiseuille flow. Fine. So this module 2 will be covered in 8 lectures. Hello. Is
Yes,
it
sir.
okay?
Yes, sir.
Yes, sir.
Fine. Now we will talk about module 3 or unit 3. Now this unit 3 is dedicated for the real fluid flows. Real fluid flows. So in this, what we'll do is we'll define one of the most important parameter or the dimensionless number in case of fluid flow called as Reynolds number of flow. This number is used to classify whether the flow is laminar or turbulent. That you will learn when we talk about this module in detail. Fine. And then we'll study the laminar flow through a pipe, then the velocity profile and head loss, how the velocity is distributed within the pipe. So what is the nature of the distribution, velocity distribution within the pipe, how the flow is developed, right? How the velocity profiles are developed in case of fully developed flow, all that stuff we are going to discuss. Then the some part of turbulent flow, that turbulent flows, then the basic theories of turbulence, then the models like eddy viscosity model or eddy viscosity theory, the Prandtl mixing length theory. These are the theories suggested for modeling turbulence in the flow. Turbulence, for time you just understand, it is a highly haphazard three-dimensional flow where it is very difficult to predict the nature of the flow. For time you just understand meaning of turbulence is this highly haphazard three-dimensional flow whose nature is very difficult to predict. Okay. Then we'll also talk about how the velocity profiles are developed for this kind of flows, turbulent flows. Then universal velocity profiles, then the velocity profiles for smooth pipes and rough pipes. Again, these are the two different ways in which you can model the pipes, right? Pipe surfaces, inner surfaces. Then one of the famous equations called as Darcy's equation or Darcy's Weisbach equation, which is used for calculating the head loss through a pipe. And again, we are not going to derive it. We'll directly talk about the final expression. Of course, I will explain each and every term in this equation, why it should be like that, and what is the significance of each of the term in this equation, and then we'll use that equation for further calculation purpose. Okay. And at the end, we'll talk about the Moody's diagram, which is used to find out the friction factor in case of pipes, and we'll study some or we'll analyze situations like pipes in series, pipes in parallels, and we'll also calculate what are the major and minor losses through pipe whenever there is flow through a pipe, right? So all what you can say, the first half of this module, real fluid flow, first half is this one is theory based, and the second half is application of whatever we study. So this part is application, right? We will solve the real life situations in this part, real fluid flow. And I'm supposed to cover this entire module 3 in 8 hours. Okay. Now coming to the module 4, boundary layer flows. This is actually a very lengthy topic, but I'm supposed to cover it in 7 hours. And the treatment for UG course is what you can say very superficial for this. However, if you go to master's program, there is separate course on this boundary layer. Separate course, I said. Okay. But for our case, we will have the superficial treatment for the boundary layer flows. So we'll talk about the concept of boundary layer, how this concept came into picture, what is the use of this concept, the person behind this concept, the scientist Ludwig Prandtl, and how this concept was breakthrough in whatever the developments we see today in case of aerodynamics. So this guy just now I named Ludwig Prandtl, who formulated this concept of boundary layer theory, is also called as a father of modern fluid mechanics. Okay, so boundary layer theory, and then different definitions and all that will be covered in module 4. Then von Karman momentum integral equation. And this guy von Karman was a student of Ludwig Prandtl. Von Karman. So we'll talk about the integral equations again without proof, and then we'll analyze laminar and turbulent boundary layers. We'll also learn how to find out the drag and lift, and how the boundary layer is separated, and how to control the boundary layer separation. What are the disadvantages of boundary layer separation? How it affects badly. So those who are inclined towards the aerodynamics part, they will be more interested in this module, boundary layer flows. So why the shape should be streamlined, and how to make the body streamlined, why to make it in that way only, why the profile should be like that, all that stuff. The theory behind the shapes we will study in this topic, boundary layer flows. So I'm supposed to cover it in 7 hours. Fine. Now the last topic of the unit 5 or module 5 is totally devoted for compressible flow. Compressible flow. Now, apart from module 5, whatever we talked about module 1, 2, 3 and 4, everywhere, even in 99% of the cases, we will consider the fluid as incompressible. Means we will not take into account the changes happening in the density with respect to pressure. We'll say that the density of the fluid remains constant throughout, and there is no increase or decrease in the density. That type of assumptions we make 99% of the times, I said, in these 4 modules. However, here in compressible flow, we'll consider the effect of these density changes. Fine. And this whole module is based on that compressible flow. Again, those who are what you can say, more inclined to the aerodynamics or aeronautical field, they will be more interested in this part, last module. So you may be knowing what is Mach number or the sonic velocity. Part of it you have already studied in 12th physics, I guess. Is it? Hello? Hello?
Yes, sir.
You must have studied part of this in 12th physics. At least you may be knowing what is sonic velocity, subsonic, supersonic, Mach number, or not. Anyway, as a part of the course, I am going to cover it in our course. So that's all about the content of the fluid mechanics. Then coming to the laboratory part. So this is a list of the experiment. You just go through the list. Overall, they have given the 9 experiments. Out of these 9, we'll be doing the 7 experiments, minimum 7 experiments. Fine. And then the important part, that is books recommended. Most of the time students ask me which book they should refer or which book I recommend. So I am just keeping the entire list on the screen. You just go through the books, and some of the names you may be knowing or not. Hello.
Yes, sir.
So the textbooks, the first textbook is written by Dr. R.K. Bansal. This is an Indian author book, and second is also by the Indian authors, Dr. S.K. Som and Dr. Gautam Bishwas. These professors are from IIT Kanpur, these two, and Dr. R.K. Bansal. People may be knowing it. Okay. So these two are textbooks. However, I am not limiting myself, or I am not suggesting you not to go beyond these 2 books. When we talk about the theory part, when I actually start our syllabus, that time you will appreciate when I bring the material on the screen, it will be, most of the material will be from these reference books. Most of the material, I said. So if it is possible for you to refer to those foreign author books, it is well and good, but sometimes student may face difficulty in understanding the contents of these books, then they can always go for these 2 Indian author books. But however, I suggest from concept point of view, it is better if you refer any of the book from this reference book list. Fine. And as already mentioned, most of the content will be from this list only. And part of it will be definitely from these two books also. These are good books, no doubt about it. Any doubt in this?
No, sir.
No, sir.
No, sir.
Fine. So that's all about the syllabus. Still we have 20 minutes, right?
Yes, sir.
So I am going to show you hardly 5 slides in those 20 minutes. And these slides will give you a glimpse of what we are going to study in fluid mechanics. Okay? Can you see my slides?
Yes, sir.
Yes, sir.
Okay, fine. So the fluid mechanics lecture 1. Now the first part of module 1 or first sub part of module 1, which is nothing but the properties of fluids. We'll talk about what are the different properties of fluids. Right? So again, I have summarized the outcomes for this particular topic, properties of fluids and the fluid statics, both together. So after learning this chapter, you should be able to, again I repeat, students are supposed to go back to those outcomes and check whether they have actually learned these outcomes or not. They have achieved these outcomes or not. At the end of the module I am saying, okay? So the first outcome which we are going to target is, see, students should be able to understand the basic concepts of fluid mechanics. Right? So this is our one of the outcome. Then the student should be able to recognize the various types of fluid flow problems encountered in practice. Mean they should be in position to segregate what type of flow it is or how to analyze the situation. Right? So they should be in position to divide the problem in what you can say the bits and pieces and analyze the situation. So that type of understanding is targeted. Okay? Then students should be able to model engineering problems and solve them in a systematic manner. Just now I talked about. So we will use a systematic approach for solving a problem, right? Means we'll talk about 4 or 5 standard steps which will be followed throughout the course and will be more or less applicable for all the cases, irrespective of which module we are studying. That's why I call it as a systematic manner. We will study everything in systematic manner. Then next, so students will be able to have a working knowledge of the basic properties of fluids and understand the continuum approximation or continuum concept. Now if you go back and refer the syllabus, there was concept of continuum, fluid continuum. So this will be a part of discussion for the next lecture, continuum approximation, because our whole fluid mechanics is based on this approximation itself, right? Fine. At least the fluid mechanics which we are studying in UG course. You may study the fluid mechanics without making this assumption, but that scope is very limited. And that type of study is not carried out in UG courses. It will be there in PG courses, definitely. So we'll be using continuum approximation all the time. Okay. Then the next, sorry. I should minimize this one. Then next is students will have the working knowledge of fluid property. The most important property of fluid amongst all properties, whatever properties we are going to discuss, the most important property is going to be viscosity. Right? Now this is one of the important property which affects the fluid behavior to a great extent compared to any other fluid property. That's why separate course outcome is given for this, having a working knowledge of viscosity and the consequences of frictional effect it causes viscosity. So students should be able to analyze that type of situation. Actually कुछ तो गड़बड़ हुआ है इसमें, मिस गया है यहाँ. Okay, let it be. So how the matter is classified, basically you may be knowing this. Even if I do not project that image on the screen, then also you should be in position to answer. How the matter is classified broadly?
Solid, liquid, and gas. What?
Any other classification? So this is how you studied the matter in case of 10th, 11th, 12th, right?
Based on the
Classification as-
molecular interactions.
Classification, the way you said just now, solids, liquids, and gases. This type of classification is given in 10th, 11th, 12th, right? However, here we are going to classify matter in two streams only. One is called as a solid and another is called as a fluid. I said fluid. Okay? And fluids are further classified as liquids and gases. Remember hereafter. Fluids are further classified as liquids and gases. So the matter is basically classified as solids and fluids. Bas. Is it clear? Hello.
Yes, sir.
हाँ, तो दो ही
Yes, sir.
classification है, ज़्यादा सोचो मत उसके बारे में. Then, now the attributes of the solids and the fluids, which are nothing but liquids and gases. So all these attributes are known to you, except the last one, which is viscosity. This one. क्या हो रहा है इसको? हाँ, except last term viscosity. Rest of the attributes are already known to you. For example, macroscopic description you already know. Then the mobility of molecules, whether the molecules are in position to move easily or not, that is known to you with respect to solids, liquid, gases. Then the typical fluid property like density, or the typical property density, which is applicable for all solid, liquids, and gases. And we know that the essentially the solids are a bit heavier, high density materials compared to the liquids, and the gases are even lighter, right? So that thing is known to us, no need to discuss. Then the molecular spacing also, we know about molecular spacing, right? So in case of solids, molecules are closely packed. In case of gases, they are loosely packed. That part is known to us. Then you must have studied what is the effect of shear stress and normal stress. Where you studied this? Have you studied strength of materials in third semester? So I hope you may be knowing what is shear stress and normal stress, right? Again, we are going to revisit these two concepts while talking about fluid statics part, the shear stress and normal stress. In statics part, we are more interested in normal stress, and in case of fluids when they are in motion, we will not talk much about normal, but we will be more talking about the shear stress. Fine. And the last property, viscosity, we already know it is. This property will be defined for liquids and gases and not for solids. We know this. This is property related to the fluid. Fine. Now next. So before we end today's session, I just want to introduce the definition of fluid. Right? Because our subject is fluid mechanics. Mechanics you already studied in first semester. Now I am going to talk about what is this fluid. So what is your idea of fluid? What do you mean by fluid? Based on your understanding of 10th, 11th, 12th, just define it.
Which continuously deforms.
Very good.
Matter that can flow.
That continuously deforms by applying the stress.
Name
shear
yourself.
stress.
Name yourself. The guy who is saying continuously deformed.
Darshan.
Darshan, surname?
Oza. Darshan Oza.
Darshan Oza. I can say that Darshan has already started reading book on fluid mechanics. I appreciate.
Thank you.
Okay. Now those who are saying the anything which flows, this is very vague definition of fluid. Is it clear? If high school students they say that anything which flows is a fluid, for them it is okay, acceptable. But engineering students should not talk in that language. So I want what you can say the engineering definition of fluid or scientific definition of fluid, right? Which is based on some fundamental background, right? So Darshan was saying that it is. Darshan, can you repeat?
Which continuously deforms by applying a shear stress.
Very good, very good. Now for all of you, I am going to project one diagram on the screen. Right, on left hand side you will see the static deformation which you already studied in SOM, and on right hand side you will see the deformation in case of liquids, right, and how it happens. क्या हो रहा है इसको? Okay, can you see this? Can you see the same slide? What is fluid वाला दिख रहा है slide? Hello.
Yes, sir.
Yes.
So you compare these two diagrams. One is for the solid on left hand side. I am calling this as a static deformation, and on right hand side we have the similar kind of diagram or the flow situation. The only thing is I am taking fluid in between this passage, and now I am saying that the deformation in this case will be continuous deformation, right? So this case you have already studied in SOM. So what do we mean by static deformation? Let us say if you have a fixed surface or a fixed plate like this, right, or you assume this as a block, metal block, right, and if you are applying some force somewhere here, so the type of deformation which will occur here, it will be a static kind of deformation. You must have studied Hooke's law. Within elastic limit, what happens if you remove this force? What will happen? What will happen if you remove the force? Hello. In case of solid, what will happen if you remove this force? Suppose your system is in within elastic limits.
So it'll come back to its original position.
So that you know by the understanding from solid mechanics or SOM, right? So now how the deformation is different in case of fluids? Look at this diagram. So let us again imagine you have the plate like this which is stationary, one more plate here, and you are applying some force at this end, and this passage is filled with the fluid. Okay? This passage is filled with fluid. Now this is purely a hypothetical experiment. Don't try to conduct this kind of experiment even at home. Get me or not? This is a hypothetical experiment actually. So what will happen if you apply force at this end? And forget about the static deformation and solid mechanics now. Talk about fluid. What will happen? Any idea?
So what? Please repeat.
See, we have a fixed plate at the bottom and we have a plate which is moving at the top. Some force capital F is applied at this end, and you are just stretching that what you can say the plate on right hand side, and this passage is filled with liquid. Fluid. Fluid le lo. So what will be your observation here?
It will flow it will continuously move.
So now you will make 3 types of observations in this experiment. I am just reading those observations. You pay attention and understand each of these points. So the first what you will observe is under the influence of the shear force, the top plate will move, right? And since fluid cannot withstand shear, now this line is important. I repeat, since the fluid cannot withstand shear, it too starts moving. Means fluid will also start moving in the same direction in which your plate is moving. This is your first observation. Clear? So the important line is fluid cannot withstand shear. Now, second observation, what you will observe? The fluid adheres to the plates. Means it will stick to the plates or not. The fluid will adhere to the plates. Means if your bottom plate is stationary, the first layer of fluid which is in contact with the bottom plate will be at rest. Reason being, the surface is at rest. So fluid is adhering to the plate. Clear? Same way, the layer which is in direct contact, top layer which is in direct contact with this moving plate, will also adhere to the moving plate and will acquire the same velocity as that of the plate. Is it clear?
Yes, sir.
Yes, sir.
This is your second observation. Now, last observation. The upper plate would accelerate. The upper plate would accelerate until a certain limiting velocity, let us say capital U, is reached or acquired. And the moment you reach that limiting value capital U, then what will happen is the driving force capital F, which is applied here, driving force capital F, will become equal to the resistance force, which will be occurring in opposite direction as that of F. So these two forces will be equal. The moment these two forces become equal, then acceleration will be 0. Is it clear? Then the plate will move uniformly on the right hand side. Is it clear?
Yes.
So these are the three observations which you will make, and based on this experiment, now we are going to define what is fluid. Right? Now, Darshan, you will help me in defining what is fluid. Shall I project the definition on the screen now?
Yes.
Fine. So this is the definition of fluid. ये वर्क नहीं हो रहा है शायद पीपीटी ये हाँ ऐसे ही देखो. So just go through the definition of fluid and then we'll stop. Read the definition and understand the words which are highlighted in blue. If you miss single word out of this, and by chance if I ask the definition in examination, I am going to give you 0 marks. I repeat, these words are very, very important. Without these words, you simply cannot define fluid in a scientific manner. So fluid is a substance which deforms continuously under the application of shear force, no matter how small the shear force might be. Is it clear? So if I go back to the previous slide, this one, so here I am not going to talk about what is the value of the force F which I am applying here, whether it is 100 Newton, 100 kilonewton or 1 Newton, right? Even if I am applying a very, very small force, the moment I apply the force, shear force, the fluid will start moving or fluid will start flowing. The reason being, we simply concluded from the observation 1 that fluid cannot withstand shear. So you should understand these words. And as who said deforms continuously?
Samir.
नाम बोलूँगा तुम्हारा.
Darshan.
Okay. As Darshan said, deforms continuously, and this is the complete definition of fluid. Throughout your what you can say the engineering, you should not forget this definition. Hereafter, nobody will tell me fluid means anything which flows can be called as fluid. I don't want that type of definitions from engineering students. Is it clear?
Yes.
So I think it is time to stop now. It is already 11:08 now. Just give me 1 or 2 minutes so that I can download your attendance and then we'll stop. Right now 61 students are there. Present. 61. So tomorrow is holiday. We have the next lecture on Friday or Saturday?